this lecture. We're going to be starting the second half of this course. The first half of the course, so to speak, was largely probability, and we were in this comfortable world of probability spaces where the experiment was very precisely defined. The random variables that come out of the experiment's outcomes are sort of well defined, and the distribution is known, and we learn to do calculations with those distributions. We will continue that, we'll keep continuing that, we will not forget that, but we will now introduce the context of statistical problems and procedures, where they come from, how they arise, how probability is sort of connected to it, and how one does statistical procedures and analyzes them is what we will slowly start. So in this week we may not fully start it, but we'll make some steps towards understanding the setup for a statistical problem and a statistical analysis situation. Okay, so this week is largely about statistics and their connection to samples, and these limit theorems which justify many of these procedures. Okay, so let's get started. So the first one is we're going to start talking about statistics from i.i.d. samples. This notion of i.i.d. samples, independent and identically distributed samples, is sort of very crucial, and we will see how i.i.d. samples are very informative about the underlying statistical phenomenon, underlying random phenomenon. So that's sort of going to be the theme, and we will look at this a bit more closely in this lecture. Okay. So it turns out we've seen i.i.d. samples before. Okay, so far in our study we have come across i.i.d. samples in multiple situations. In fact, 3 situations, as I can recall, we have already come across i.i.d. samples. The first one is when we studied Bernoulli trials. Okay, so you can see I've forgotten the R here. So let me just add the R. It's Bernoulli trials. So when we looked at Bernoulli trials, we saw i.i.d. samples as in something that was independent and identically repeated, and we saw outcomes or random variables from the experiments, and what we got was a series of samples of the same random variable, same distribution, but independently repeated. We saw that in Bernoulli trials, right? So the experiment keeps repeating, and we look at the success. I'll describe this in a little bit more detail. Another place where we saw it was Monte Carlo simulations. So even there again, we would run a probability experiment over and over again and try and find out something about it. And the third part, maybe you never thought of it as an i.i.d. sample, but we worked with data, samples from the data, and then we computed histograms, and even there we were using i.i.d. samples. So I'll come back and talk about these 3 later on at the end of this set of lectures, but we've seen i.i.d. samples before. In all 3 instances, we could infer something very useful from these i.i.d. samples. So let me go into some more detail on each of these scenarios and show you how i.i.d. samples occurred and what information or statistics did we glean from it is what we will look at in the next few slides. Okay, first let's start with Bernoulli trials. In Bernoulli trials, we have an experiment and there is an event of interest. In that experiment, there's only one event we are interested in. We are not interested in other events. We want to know if that event happened or not, right? So we think of the occurrence of the event A as a success, and if it did not occur, it's a failure, right? And one of the information or the statistics that we want from such a observation or trial is what is the probability of the event. So maybe we are interested in that. We are interested in is whether it's high or low, or maybe even the exact value. We're interested in that, right? So this is what the setup is. And Bernoulli trials are nothing but independent repetitions of an experiment, say n times. So now we can associate a random variable with each of the Bernoulli trials. Notice how I do this. This is a random variable which is usually called an indicator random variable. It indicates whether an event occurred or not. In this case, it indicates whether A occurred or not. So if xi I define as the random variable which is equal to 1 if A occurred in the ith trial, and it is 0 if A did not occur in the ith trial. So that's the definition for xi, you can see it's a Bernoulli distribution, and it takes value 1 with probability of A, that takes value 0 with 1 minus probability of A. And for different values of I, these random variables are independent. Okay, so you have x1, x2, so on till xn. These are independent and identical Bernoulli samples. Okay, so notice how from the description of Bernoulli trials, we are able to come to an i.i.d. sampling situation. Okay, and from this we could glean a lot of information. In particular, we are interested in finding the probability of the event A. Now, for instance, prevalence of the disease in a population. If you remember, this is how I introduced Bernoulli trials. So this is something that's very useful. Okay, so once again, i.i.d. samples. We've seen these Bernoulli trials before, and from the i.i.d. samples, we want to get or glean some information or statistic that is hidden about the underlying statistical phenomenon. Okay, so this is one example. A very similar example is Monte Carlo simulations. I want to go through this a little bit fast. So there is again an experiment or event of interest. This is typically too complicated for you to write equations with. So we ended up writing some programs, and even if we did some analytical calculations, we wanted to check if it's correct or wrong. So we wrote a program, simulated it, and then repeat the simulation multiple times independently, and that's crucial, right? You have to repeat the same simulation over and over and over again, and hopefully independently. So the computer had some way of generating some random things, and we assumed they were independent, and we repeated it multiple times, and we figured out how many times a particular event A occurred, and we measured the probability of A as approximately NA by N. Okay. So again, you might wonder, why is this true? So this is sort of like the bedrock of probability theory in some sense, right? So you want to think of the probability of an event A as some sort of a frequency with which it occurs, right? If somebody says probability of A is 10%, right? And if you observe the experiment 100 times, you pretty much expect that around 10 times, maybe 9 or 11 or something like that, the A must have occurred, right? So only then it becomes meaningful to talk of probability in that sense, right? So this interpretation of the probability as being the frequency with which it occurs, so the number of times. So particularly if you repeat the same experiment over and over again, independently multiple times, then the fraction of times the event A occurs should roughly be assigned as the probability, right? So this is what we hope we are doing in our analysis and all that. Okay. So I want to point out that this is very important. This is sort of foundational in some sense, and from our theory, it should turn out that this is true, right? So if you repeat the experiment multiple times and observe what fraction of times A occurs, it better be close to the probability that you assign to it, right? So in the theory, it should be complete and closed in that fashion. So this is something that we should try. Okay. Now this value of n is very, very interesting and important, and you may want to say, if n were 100, I am going to be this close to the probability of A. NA by N will be this close to the probability of A. If n were 1000, I will be this much closer. If n were 10,000, I would be this much closer. I want to make some statements of that type, so that I know that my statistical procedure is working correctly and things like that. Okay. Once again, in this situation, we have i.i.d. samples. Okay. It maybe it doesn't look immediately like i.i.d. samples to you, but you can again define an indicator random variable exactly like we did for the Bernoulli trial. Xi is the indicator for A, and then you line up x1, x2, xn. These are i.i.d. samples, right? So notice most often in statistics, and when you want to compute some information about a statistical phenomenon, i.i.d. samples naturally get involved. Okay. So let's come back finally to computing histograms. This is something that we did for continuous models, right? So when you wanted to model a random variable as continuous, and usually you looked at some n data points, and these data points, like I'm denoting them as x1 to xn, and then you binned these data points, right? You defined maybe a bin of suitable thickness, and then you said the a comma b is the interval of the bin, and then you counted how many of your data points fell inside that bin, right? So that was something that we counted to make the histogram. And if you want to model this data as coming from a continuous random variable, and you want to do calculations with that, then normally you had a density for that continuous random variable, and if you're given the event A as falling in the interval AB, you know that the density when integrated from A to B will give you that probability. We know that much about the histogram and the probability involved in it. Okay. So, the data points themselves, once again, in this scenario, are usually thought of as i.i.d. samples from the density fx of x. Okay, so each xi is continuous and it has density fx of x. It's a random variable. So, the observations of these random variables are thought of as the data points, and then from there again, you expect that the probability that x lies between a and b is number of times your data point fell in that bin AB divided by n. This is your density histogram, isn't it? So, you expect this to be sort of true. Okay. So, here again you see you have i.i.d. samples. So, it turns out every time we were trying to get some information from data or doing an experiment to gather some statistic, we were actually using i.i.d. samples. Okay. So, this notion of i.i.d. samples is very, very important and crucial. That's because in the way we think of the theory and the way we think of data, i.i.d. samples hold information about the underlying distribution. Okay, so this is something very important to convince yourself about and be convinced about, and it's sort of easy to see also. So every time you don't know the distribution, so you're hoping to repeat and repeat and repeat till you get enough data to have some method of getting what you want from the data. And this notion of an i.i.d. sample is very, very important. Every sample should, first of all, why should it be identical? It should be identical because only then the same statistic you measure will not change, right? So you can hope to measure. Why should it be independent? You should not get the same value over and over and over again. Then you don't learn anything about the distribution, right? So it should be independent and it should be identical in some sense. It cannot be all over the place, then you don't get any meaningful information from it. So there's various ways to think of why i.i.d. is very informative, and I will leave you to think about why that's important, but i.i.d. samples are really the bedrock of statistical procedures. Okay. So usually, as we saw in the previous three scenarios, you're given one particular sampling from an i.i.d. sample model, and you want to get some partial information about the distribution, about maybe probability of an event, maybe the PMF, maybe the mean, variance, whatever you want about the distribution that underlies the samples. Okay, so this is common to all the three procedures that we saw before, and this one can sort of generalize, and that becomes a typical statistical procedure and problem. So data that you obtain is usually modeled as observations from i.i.d. repetitions of an experiment, and then your goal is to glean some statistic from that data. Okay, so unknown or partially known distribution. You may have some idea about the distribution. You may not know anything about the distribution, right? What can you get from the i.i.d. samples is very crucial. Okay, so we'll see quite a few examples. So first example from the data world I can think of is the iris data, right? So we saw the iris data set. There was this data about every iris. So supposing instead of giving you 150 different irises, I gave you the same iris data over and over again. If it were the same data, then you don't get any information about the distribution of the the sepal length, sepal width, and petal length and petal width, right? You don't gain any information at all. So the data needs to be independent. It needs to be different irises. Now, instead of just focusing on iris plant, supposing I look at iris, next time I look at rose, next time I look at I don't know, name your favorite flower, lily, this lotus, this, that. You keep on changing the flower. Then again, there's no hope of you getting any reasonable information from that. It has to be the same distribution, so irises, but different irises, so that you get independent information about the same phenomenon. Okay, so if you want to model that natural process by which the iris flower blooms and its petals form and the length and the width of the petals and sepals, etc., you want to model that as a random statistical phenomenon and study it, you should look at enough independent and identical occurrences of that in nature, measure, get the data, and then try and glean some statistic from it. Okay, so it's sort of easy if you just think about it, but you have to now do a model and then do calculations, and all of that will enter the picture, probability will enter the picture, but that's the underlying situation. So keep this kind of an iris in your mind when somebody describes a statistical process to you, and the same thing continues, and any statistical problem is like that, right? So there is an underlying natural phenomenon which creates some observations, and you hopefully want to get independent, identical repetitions of that same event, and then you want to get some statistical information from it. Every single data we look at will be like that. Okay, so that's the idea. Okay, so so in general, the way we do our analysis will be, first of all, how to have metrics for your statistical procedure. Any procedure or process or thing that you come up with, usually there'll be a metric for how good it is, right? So you have to decide how to measure goodness metrics is important. And then the second problem which is interesting is, how is the goodness metric connected to the number of samples? Okay, and these two are very important. Number of samples is very important. Goodness metric of your statistical procedure is very important. So keep this simple slide in mind as we study more and more statistical processes. Even your, whatever learning algorithm you may call is, at the end of the day, it's like a statistical procedure, right? So you always want to think of this as the basic underlying phenomenon. Okay, so let's keep proceeding. We're only taking baby steps now. This is a very high level picture. We will get into more details as we go along. Okay, so here's immediately an example. Okay, so I'm going to start with a very simple example where somebody gives you 20 IID Bernoulli P samples and P is unknown to you. Okay, so this is actually a very simple situation in today's complicated world of statistics. We've been doing statistics for more than 100 years now, very formally, so it's very advanced field. So this is maybe a very basic example, but still you should have enough clarity about how this basic example comes along. Okay, so I'm going to give you 20 IID Bernoulli P samples and P is unknown, and maybe the goal is to try and find P from the IID samples, right? So it's a reasonable goal one can think of. Okay, so the first thing to understand is, what I'm going to give you is 20 IID Bernoulli P samples. I keep calling them samples, but at different points in time, you may get different samplings as a result of the sample. So today, if I were to give you 20 IID Bernoulli P samples, I may give you the sampling 1, okay, 1 1 0 1 0 0 0. I may give you that. Tomorrow, if you were to come and ask me, I may give you sampling 2. Okay, so because the process is fixed, every number I give you is Bernoulli P distribution. That's all. But the exact sequence is not fixed at different points in time. The same samples may actually give you something different. Okay, so there is a difference between samples and the actual instance of the sample, or samplings as I'm calling it, and this difference is very important for you to keep in mind. Okay, the IID samples, you will describe them as capital X1, capital X2, capital Xn, distributed like the distribution of X. You will say something as simple as that. So that is your distribution. So the IID samples distribution remains the same, but at every sampling, I will actually get different data. Okay, I will get a different set of data. Now, it's important for your statistical procedure to work with any particular instance. Your statistical procedure, supposing you develop a statistical procedure for finding P from the samples, it should work for sampling 1, it should work for sampling 2, it should also work for sampling 3, or maybe sampling 4, sampling 5, sampling 6. Whatever samples I come up with, as long as I am faithfully giving you IID Bernoulli P samples, your procedure should give you the exact same answer. So the samples are actually random. Okay, so that's the most important thing one needs to assimilate, and that's why I put out this example explicitly. It may be clear to you, but once again, it's important to see that the samples are random. They are not fixed at any point in time. So, but P remains the same for every sampling, but the samples do not remain the same. So over time, if you sample today, if you sample tomorrow, you're going to get different samplings. Okay, so the only thing you're guaranteed is each sample is an observation from the distribution Bernoulli P. At least in this case, that's what is given to you. Okay, so the statistical procedure should give you, I mean, if you design it well, it should give you the value of P with some guarantee on, okay, this is how close I will be to the actual P. for every single sampling it should work. So over any sample it should work in that fashion. Okay. So now often in statistics, and as we study more, in a few more lectures, I myself will use the word samples for everything. I will use the word sample for the random sample x1, capital X1 to capital X2 to capital Xn, and every instance of the sample I will also say simply sample. Okay, I will not say sampling or anything like that. Okay, maybe we will write small x1, small x2 for the actual samples, but usually people simply write capital X1, and there is this understanding that you know all this, in, sort of internally you know this, so we don't have to repeat it. So this danger of mixing up samples and samplings is there, and usually it's usually clear from the context, so people don't make this big claim. So later on you will see I will also do that myself. I'll be guilty of that same mistake, but keep in your mind, when I say i.i.d. samples, the samples are random, and every instance of the sample can be different, and for every instance your procedure has to work. Okay, so that's important. Okay, so now having said all that, having given you examples and some settings, etc., I'm ready to sort of define what a typical statistical problem or a procedure will look like. Okay, so you will usually have a model for the samples. Okay, so you're observing some samples. You will usually have a probabilistic model for the sample, and that will be written in this fashion. It will be a i.i.d. samples, x1, x2 to xn are i.i.d. according to the distribution of a random variable x. So what does that mean? Okay, so that's what this thing is. This is i.i.d. according to the distribution of x. So if x has, let's say x is discrete and it has a PMF px of x, let's say, okay, each xi has PMF px of x, the same PMF, and xi are independent. That's what this means. So when I write like this is how you read it. Okay, so you have a random variable x, and that's defined for you. And if I say i.i.d. samples from the common distribution of x, or i.i.d. x, if I simply write it like that, I mean every xi has the same distribution of x. So if x were to be continuous, let's say it's normal 0, 1, then of course each xi will be continuous and it will have the same density as x, and they will all be independent. So if you want to do any joint distribution, you can simply multiply the marginals and you will get a joint distribution. Okay, so that's the model for the sample, and the model for the samples is probabilistic. So that's where the probability will come in. Now you will be given data, right? So the given data we will assume is one sampling instance from my i.i.d. sample model. Okay, so somebody generated this data and gave it to you. Okay, according to this model, we will assume it's according to this model. It may not, the model may not exactly match. Our model might be approximate in many ways, and in many cases real life data you may not be able to even model, right? So but the model will be usually close enough, and that's enough for your statistical procedure to be developed and for it to work. Okay, so usually the distribution that we assume for x will be partially known or it will be unknown. Okay, so unknown is okay, some distribution we don't know. What is this partially known? You may know the nature of the distribution, but you may not know the parameters of the distribution. So this is the most common assumption. So I might say x is Bernoulli, p, and p is unknown, like we had in the previous case. Or I might say x is normal with mean mu and variance sigma squared, and mu and sigma squared are unknown. Okay, so this is very, very common. Or x is Poisson with parameter lambda, and lambda is unknown. So things like that one may assume for the distribution of x, and that parameter will be unknown. Okay, so the goal usually in a statistical procedure, in a statistical problem, is to find develop procedures to find more information about this missing information about the distribution of x. Okay, so if a parameter is missing, how do you find the parameter? Okay, or if something else is of interest to you, so you may not really care about the parameter, you may care about the probability of an event. Okay, of course if you find the parameters, you can find the probability of the event, but that may not be the best procedure, right? So supposing you have to go in 2 steps to some answer, Maybe there is a direct step which is better, right? So we have to design all that and define all that when we do statistical procedures. Okay. So in general, this is how at least statistical problems in this class are going to look like this. So what type of information you may be interested in? Mean of x, variance of x, maybe. Okay. Maybe you are interested in probability of an event involving x. Maybe you are interested in the distribution of x, or maybe you are interested in something more, more, more complicated to think of, or maybe the size of the range of x, right? So you may be interested in things like that. These are all a little bit more complicated, and different types of information one can think of about the distribution that is known or partially known. Okay. So this is a typical statistical problem, and you can see how probability enters the picture. You can see how data enters the picture, and you can see how your comfort with knowing probability is going to help you in designing statistical procedures, at least in this kind of a scenario. Okay. So this is a typical statistical problem. Okay, so that concludes this lecture. I don't have any problems to solve with this lecture, but hopefully you got an idea of how statistical problems arise, how i.i.d. samples arise, and how i.i.d. samples hold information about the underlying distribution. And we will see more and more examples as we go along, maybe not in this lecture, but from the next lecture, next week onwards at least, we will see many more precise, specific statistical problems of this nature, and we will try and develop some procedures and provide some guarantees. Okay, thank you very much.